Hello viewers and welcome to a new STM32 World tutorial video. A few videos ago, by now, I made a video about I2S or I2S with DMA making a sine wave on one of these audio devices. I've had a lot of comments in earlier videos why I didn't make a video with a complete project rather than videos about individual elements. And it is, of course, because it is hard to put all these things together. But this video made me realize, and by the time this video gets released, I will already have released this video, which has not been published yet, where I plan to make a music player, because technically speaking, I have all the elements, so it's just a matter of putting those elements together. But let's look at the last video, which was the I2S DMA dual sine. I was running that on this board, the STM32 F407G Discovery 1 board, which have an I2S audio DAC down here. But as this video documented, I really think the design of this discovery board is quite brain dead. So I decided to reset and go back and actually use my STM32 World board instead for these videos. So I have started a page on the wiki called STM32 music player. It's very much a work in progress at the moment, but it will get there. And essentially turning one of these devices into a music player, there are at least a minimum of 2 steps that are necessary. First of all, we need the audio device. I will use this PCM5102A module, which is a Texas Instrument audio DAC. These boards, it's documented in the last video, they are very readily available and quite cheap. We're talking $4 or $5 tops for one of these boards. So that will be one step. The next step will be actually read audio files from an SD card, and the final step will be then to pass those audio files and then put it all together. Further steps could be to add some buttons so you can actually control the player, and perhaps add a display so we can actually see what file is playing at the moment, and information like that. Maybe make a cool visualization of the video. I don't know, I haven't made those plans, but for now I think it'll be 2 videos. In the first video, in this video, we will be looking at this PCM5102 and essentially do the sine wave of that to make sure that we have the communication out on it. And then in the next video we will probably be looking at parsing the WAV files, read the WAV files from an SD card and pass those WAV files, and hopefully we will end up having a really cool music player in a couple of videos. So that is about it. So let's start by looking at the code. So the original earlier video, which I did this dual sine wave on I2S on the STM32 F407 Discovery board, we have the code here, and what I have done initially is essentially to clone this module and then change it or copy it, create a new one, which is running on my STM. So avoid confusion, let's close that. So on my STM32 World board with one of those PCM boards attached, I will be running that today. Just to be clear, my STM32 World board is documented on the web page, so you can see the specifications there. I will be using this board, which is essentially an STM32 F405 clocked at 16 megahertz, and it's very bare bone. So I'll be using that today. Now, let's go through what this is, and at the moment it is essentially exactly the same as the old one. So let's look at hopefully that will load fast enough. I should have loaded that before I started this video. When will I ever learn? Here we go. Let me go away for a second. So essentially, the STM32 F405, I have enabled a LED. I have a button. I have the UART as usual. I have the single wire debug, and I have the I2S pins down here. And it's only a matter of 3 pins. There's a clock, there's a data stream, and there is a word switch or whatever, so that will switch between the 2 channels, because this one is a stereo DAC, so there are 2 channels coming out of this, left and right. Now if we look at the setup, everything is pretty straightforward. The clock configuration 16, I have fiddled around with these and I ended up with an I2S clock of 120 megahertz down there, because that gave me the least amount of error. And if we look down at I2S, it is simply a half duplex master, all default settings, 16-bit data. I'm starting with 96 kilohertz, and I have enabled DMA, and that's about all there is for that. If we look at the code, and I think I'll go through the code and explain it, just in case I missed something in the earlier video. But I will recommend, I will recommend you go down, you go back and look at the earlier video. It's always, I might miss something in this video, so I would always suggest you look at the earlier videos. But let's go through the code of this sine wave, dual sine wave generator. So first of all, I have defined tau, which is 2 pi. Somebody pointed out to me that that is actually defined in the math library, and indeed it is defined as, I think, m pi, something like that. 2m pi or something like that, but it is a multiplication of pi, and I don't want this to be calculated, so I might as well give it a constant. Somebody pointed out that the optimizer of the compiler would take care of that, and that is quite likely that that is correct. Then I have sold a number of samples, and I want to create 256 for each channel. So that is 512. So I'll take the number of samples, multiply by 2, and then I do a double buffering. So while one buffer is being sent out to the device, the other buffer can be calculated, and that I have explained in multiple videos earlier. Pretty much look at every single DMA video I've done, and I have done quite a few, and you will see that double buffering. I also set the sample frequency to 9600, and I put this output max because I'm using 16-bit values, so that's 65,000 and something rather, and half of that would then be the max, because these are plus minus value. It is integers, it's not unsigned integers that the I2S device needs to receive. I have, in order to play audio files, audio WAV files can be defined in different sample frequencies, and rather than resampling those WAV files on the fly, it's easier to simply change the frequency of the I2S device and that is the values I have here. I create an array with pretty much all the available one. There is a faster one, I think 100. Actually, look that up. Open declaration, so you can see there is actually 192K, but for audio that is pretty much irrelevant. Even 96 is pushing it, but 96, it's okay. I have a floating point array 1, 2, left, right. So the two channels, I can set different frequencies on these two channels. I have an angle that has been explained earlier. I'll explain it shortly. And an angle change that will be calculated based on the frequency. And then I have an amplification multiplier here. Now, if you looked at the last video, that module actually had a built-in amplifier where you could use I2C to change the volume. This one does not. So the only way to change the volume is by changing the amplification. Then I define my DMA buffer and a few other variables, bits and bits that I'm using. I have my usual redirect printf to the UART, and as you can see, I have the terminal running down here, so let's look at that later. Then we have these process buffer and I2S callbacks. I'll get back to those. And then set angle changes. I calculate that angle change based on the frequency multiplied by tau divided by the sample frequency, which I look up in that array. And then I have a function here to change the I2S frequency, and that is actually a little bit annoying, but you have to stop the DMA, de-initialize the I2S, change the initialize handler, re-init it, and then calculate those angle changes and then start the DMA transfer again. That's the only way to do it. Down in the main code, I just start the DMA, and that is pretty much it for now. So let's try to first build this project. It builds, and then let's try to run it and show the output. So I will go here and I will show there, and we can see it actually shows the two frequency. One was 220 and the other one was 440. Where are we? We can do this one. No, I want to do this. And then I want to show the output here. We can see that this one actually changes the frequency every 10 seconds. I try to change the sample frequency, and that happens down here in the code. Next frequency, it just goes through that array and it picks a new sample frequency and use that set I2S frequency from there. And the interesting part is, if we look at the device, you can see even when it changes the frequency, because I stopped the DMA transfer briefly, you can see that there is a little whoop, it flips around on the scope because it actually stops very, very briefly, but then it starts again. You will also notice that it'll take a little while. One of the frequencies actually don't work. I have no idea why. It is the 22 kilohertz does not work. It doesn't send. Let's see, it should come up next. 44. No, two more. So 44,100, and then it goes to 32,100, 32,000. And now you will notice that when it flips to 2250, I think it is, 2250, the output disappears. So for some reason, that does not work. At the moment, I have no idea why that is, so you'll just have to live with it. But you will see that it actually generates, these frequencies are quite low, so it pretty much generates a very pretty sine wave in both channels, even no matter if you run a very low sample frequency of this device, just to verify that all the calculations work. So let's try it. So we keep the 220. Let's try to change this one to 880, but let's make it half. So rather than 1, 0.5, we should see. I'll run that. I'll zoom in. So there. And we can see that the high frequency is now lower amplitude and much faster, or double the speed than it was before. So it pretty much works beautifully. I've done this before, but let me explain one more time what is actually happening here. When you're using this DMA transfers, you will always double buffer. That means that we handle half of the buffer is being sent to the device, then you can calculate the other half, and then when the first half has been transmitted, it switches to transmitting the second half, and at that time you can calculate the first half of the buffer. In order to facilitate this in your code, there are two different callbacks. There is a TX half callback, which is being triggered when you're halfway through the buffer, and there's a TX callback, which is being triggered when you are fully through the buffer. And all I'm doing here is I'm calling the same process buffer function, but with a different starting point in my complete DMA buffer. You can see down here when we are halfway through, that means we start sending the second half and we can calculate the first half of the buffer. That means we process buffer I2S DMA buffer 0. And now up here, when it's complete, we need to calculate the second half of the buffer, so we pass the halfway point to deal with that. In the process buffer, and I'm not going to go through this in complete details, but it is really simple. It just goes through this number of buffers, and it will calculate the two channels by adding, you find the angle, and you do cosine of that, and multiply by the amplification and multiply by output max, and that is it. And once we are all the way through, we start all over again. So we just keep circling around between 0 and tau. Tau is 2 pi, so it will just keep cycling around there depending on the angle change, which is calculated based on the frequency. Now let me actually optimize. I mean, this is pretty much what I did in that earlier project, exactly the same. So let me optimize it a little, because I had a few comments on, I think it was either on our Discord. There will be a link down. I have to do it like that. There will be a link down below, but you can join our Discord server. And I think it was a question on the Discord server whether it was acceptable to do all these calculations in the actual interrupt handler or callback routing. And whoever did that comment is right. I mean, you should do as little as possible in these callbacks, because it could clash with other interrupts. So the less you do in this, the better it is. Now, it is okay if there's nothing blocking. I mean, this one is fairly predictable, and we know that there are no overflows because we keep track of that. And it's still got, let me show you that, it's still got plenty of time to loop around in the main loop. That is my loop counter down here. So and you exactly couldn't see that because I was in the way. I wanted to show here, so we have the loop counter down here. So it has plenty of time to cycle around in the that. But I mean, fair enough, the less you could do, and I just realized there is actually, I mean, we could easily move this down to our main loop, which is probably a better way of doing it. So let's try to implement this in this. So first of all, I need to be able to trigger that calculation, and what I could do is we have our DMA buffer here, and I could introduce a new pointer here, which is DMA buffer to fill, which I start by setting to 0. That's not necessary because it's a global variable. It will be 0 initially. So what I will also do is I'll delete these two because they're not really needed if I do it in the main loop. So down here in our process buffer, I'll comment it out instead. So I'll comment this out, and then this main bit, let's comment that out, and instead we will say DM, what did I call it? God. DMA buffer to fill. Here, a buffer to fill equals, and it will be equaled the address of pretty much that. We can copy that line, and then we can go down here and say and that will be a big fat. So so this is basically, rather than calling this function up here, we just set that DMA buffer to fill equals the address that we want to handle. So now down in our main loop, which we have here, we can simply add a check. Say if this one, remember it is 0 by default, then we need to do something, and once that's done, we set DMA buffer to fill equals 0. Actually, we might want to do that first. No, it's fine. We just set it to 0 when we're done. Now all we need to do is to call our process buffer with the DMA buffer to fill as a parameter. So in other words, if the DMA buffer to fill is a pointer that points to the buffer that we need to calculate next, and that is being set by the callback. So the only thing the callback does will be to put an address into this DMA buffer to fill, and then the main loop will then immediately after call that DMA, the process buffer up here, which is identical to the way it was before. So let's try to see if that will build. It did not. There's an error here. Yes, I removed device overrun. I think I have the other two. I might not have those anymore. Never mind. Let's remove all that and just have the two, so we can remove these. So that's pretty much it. Now it should maybe build. That's fine. It builds. So let's try to run it, and let's look at the device. It works exactly like it did before. If we look down here, you can see that the output is pretty much, it loops a bit slower because now there's an extra check every time it loops through. These checks are expensive because they are executed very frequently. And I mean, that could of course be optimized by, yeah, well, could be optimized maybe, but I haven't bothered doing that. So now, but anyway, now the interrupt does absolutely nothing except setting that, and then the DMA process buffer is called from the main loop. It is possible that we could inline this to make it execute a little bit quicker, but I don't know. It shouldn't be necessary. So, of course, when we want to turn this into a music player, right? These, so just to explain what is going to happen when this becomes a new music player. This will be exactly the same, but rather than DMA buffer to, DMA buffer to fill, it could be exactly the same, but then the process buffer will be different because rather than calculating a sine wave, we need to read samples from our WAV file and then throw those WAV data out on the I2S device. But we will be looking at that in the next video, most likely. So this is the foundation for our music player, and well, we'll see if how good this becomes. One of the problems I have at the moment, I realized, is that I don't think you can hear this with my microphone. I don't know. I think my noise cancelling headphones don't pick up that that little stupid speaker I have there, so I might have to rig up another microphone or something like that. I will look at that. I will look at that in the before I do the next video. So as usual, if you like this video, please like and subscribe down below. You can also give me a super thanks if you feel like it. That would be very much appreciated. I don't really make any money from making these videos, but a bit of support would be nice. You can also please comment down below, especially in this series, because I want this to end up with like a functioning movie music player. So ideas are very welcome. As mentioned in the previous video, I think I am going to consider putting on a display. I'm going to consider putting on some buttons, and there might be other ideas. So please let me know in comments below what you would like to see. As usual, please have a wonderful rest of the day. Bye bye.